I don't think there are any up there, but I will attempt to try and make that happen more. So equivalent statements and mathematical logic. So the first statement I've got here is that two statements may be connected and either, so there's two options here. One is that one may imply the other, and two is that they may be equivalent. So I know that probably sounds a bit confusing, but either one of them means the other one is true, but maybe the converse is not true, and I'll talk to you a bit more about converse in a second. One may imply the other, but the other may not imply the first one, or they imply each other. And if they imply each other, then they're called equivalent statements. So I've got that example there, P, Q and R, such that X exists in the natural numbers, and the statement P is that X is greater than 40, the statement Q is that X equals 57, and the statement R is that 2X is greater than 80. So I can see in this one that Q implies P. So if Q is true, if X is equal to 57, then P is also true. Do you agree with that? Yes. Okay, so given that, we've got an implication here. But P, oops, so let's just move down on me. P does not imply Q. So given the number is greater than 40, it does not necessarily mean that the number is 57. So we don't have an equivalent statement. We have option one. Q implies P, but they don't imply each other. I'll just close the brackets on this implication. What we do have though, and have a look at this closely, P implies R, and R also implies P. So actually P and R are equivalent statements. They imply each other. If P is true, then R is definitely true. And if R is true, then P is definitely true because you can see that they're the same statement, it's just R is not fully simplified. So that means that these two are equivalent. And we go back to like the common contextual examples. For example, last lesson we talked about so my statement P was I'm in the pool, my statement Q was I'm wet. So if I'm in the pool, that implies I'm wet. But if I'm wet, it doesn't imply I'm in the pool. So they're not equivalent statements. If I'm wet, I might be in the shower, or I might be in the rain outside at the moment. Or maybe my maths specialist class just threw a bucket of water on me, or something like that. Don't get any ideas. Before you do get any ideas, I wear hearing aids that are worth $7,500, so don't get any ideas.
How do you go to the ice bucket challenge?
Yeah.
Surprise ice bucket challenge.
$7,500. Isn't it like 2016 ice bucket challenge?
It's every year.
Is it?
ALS is like ongoing concept.
So there's my conclusion. Q implies P, and P and R are equivalent. And we have here, this is the converse definition. So if P implies R, the converse to that is that R implies P, and if that is true, then you have equivalent statements. It's very easy numerically. So if you've got a numerical or an algebraic statement, it's usually quite easy to determine equivalence. But contextually, it's not so easy. You've got to be really careful to not fall into the trap, not that you would for this one, but to not fall into the trap that if I'm wet, therefore I've been in the pool, is a true statement, because it's not. There are other situations you might be wet. So that's the important thing here. Q and R, I've got that as part 3. Are Q and R equivalent statements, or does one imply the other?
Equivalent. No.
No, they're not. R does not imply
R, but R does not imply Q.
Yes.
Okay, so Q implies R, but R does not imply Q. So they're not equivalent. There's just an implication. Now you might get some statements where there's no implication either way. So just don't think that if you get two statements, one has to imply others as a minimum standard. That's not the case. So for example, just very anecdotally, let's say we've got the CAC fair, and I might make the statements that there are, trying to think one where there's no implication. So, well, there are more red cars driving past the school on a Sunday than normal. and there are more white cars driving past the school on a Sunday than normal. So if I say P is more white cars than usual and Q is more red cars than usual, just because there's more red cars, that doesn't imply there's more white cars. And because there's more white cars doesn't imply there's more red cars. But if statement R was the college fair is on, that implies both of those things. That will imply that there's going to be more white cars and more red cars driving past the school. So they might actually co-depend or be co-implied by some other statement. And that's all right. So you might get two statements that are even closely linked. And I'll take questions in a second, your other option, the flip side of that is two things that aren't even closely linked. So for example, I could say that tomorrow morning I plan on walking to school, and then I could talk about a certain person called John Williams who lives in Edinburgh, and tomorrow morning he plans to walk to his school and he's a teacher. There's no link there at all, and they're geographically completely disconnected. So just be careful, that sometimes you can have disconnect. Yep.
When you said that there's a state college fair on, that implies that there's more red and white cars. How can you ensure that there's going to be red and white cars?
Well, I can't ensure. I was clutching at a contextual example. But thank you, Max. Is this the same situation as, you're not wet if you get in the pool because you could be wearing a dry suit? Thanks.
Exactly.
Yeah. But I live in a bubble. Okay, so if we want to prove equivalency, so this is what you'll be doing. You'll be proving equivalency. If you want to prove that two things are equivalent, then you need to prove that P occurs if and only if R occurs. That is the proof for the implies statement. So P if and only if R occurs means that R implies P, and R if and only if P occurs means that P implies R, and then if they imply each other, you get equivalency. So that's what you're looking for. That's your proof that you're looking for. And I've got some steps here. If and only if, IFF is just a shorthand for if and only if, and you'll notice here this is the equivalency, and we get equivalence sign used as equal signs in proofs, so I'll show you that in a second as well. And I've got an example 7 now, which I'm going to go through in a second, but I know people are writing stuff down, so I'll let you write that down. So example 7 are the statements P, X and Y are rational numbers, and the statement Q, X plus Y is rational. Are they equivalent? I'd like to take votes. Who thinks that they're equivalent? Yes.
Me.
2 half people. Okay? 3 half people. Who thinks they're not equivalent? Who thinks they're too scaredy cat to vote? Thanks.
They are equivalent.
I told you. What does P imply? Q implies P, so they are.
And there's example B as well.
Yes, they're equivalent. Wait, so
Yeah.
what does it say after also, where it says steps in proof? To the right.
That.
To the right.
Oh. Is that all right? Okay, so let's talk about example 7. I've just made a bit of space. I'm going to make a little bit more. Example 7 are the statements. So this is 7 part A. Are they true? To show the steps in proof, to show that they are true, we have to show that P implies Q and also show that the converse is also true. Right, ladies and gentlemen, let's bring it back together. Sorry for the interruption.
So it'll be a negative. It's a negative.
I'm going to show that P implies Q first of all. So let's imagine that two numbers, X and Y. So this is example A. Let X equal A over B, such that A and B exist in the integers. So that's the this is the definition of a rational number, by the way. Has to be able to be written as a fraction. and let y equal c over d, such that c and d also exist in the integers. So that's the next proof. Can we imply, or can we show that p implies q by showing that x plus y is also rational, i.e. x plus y can still be written as a fraction? And the answer is, in this case, yes, because x plus y is equal to a over b plus c over d, which is equal to AD over BD plus CB over DB, and that's equal to AD plus CB over BD. And if A, B, C and D are all integers, then AD plus CB over BD is a rational value. It might be a decimal. When I say decimal, it might be not a whole number, but it's going to be rational. It can be written as a fraction. So we've shown that P implies Q. Now we have to show the converse, and I've got to make a bit more space. I'm going to have to make a lot of more space, I think. Might just make it all now. Okay, so I'm going to show the converse now is true. Can we show that Q implies P? That if x plus y equals A over B, where A and B exist in Z, that x and y are both rational numbers. Any thoughts? How do we split a fraction up to show x and y are both fractions?
X plus y equals a over b. A exists in integers.
What about this? What if x was equal to 1 plus root 5 and y was equal to 3 minus root 5? What happens then? What happens when you add those two together? It'll just be 4. So in this case, x plus y equals 4, which is a rational number. But x and y are not rational numbers. They're irrational. So we've actually just shown by counterexample that Q does not imply P. So therefore, these are not equivalent statements. And I understand, because I can see some of you might be thinking, okay, all right, that's all good and well, but if I get this question in the exam, I may not come up with that counterexample, and I see that. And so in your exam, the good news is that next year there's not as much proof in Unit 3 and 4. There's a little bit, and it's a little bit more routine. But there will be some of this in your exam next term, but I'll make it, it'll be doable. So there won't be any great leaps that you have to make. But hopefully you understand, you can see that. In the exercise in your textbook, you may have to come to those leaps. And you might have to come to those by trying, leaving, trying, discussing in a group, and then working it out from there. These are the leaps that help us produce these kinds of proof. So Q implies P is not true. Q does not imply P, and therefore Q and P are not equivalent. So P implies Q, but Q doesn't imply P. So there is an implication statement, but they're not equivalent. Jan?
Can we scroll up a little bit? I missed some of those.
I certainly can. So the next question was, are the statements P, x cubed is greater than 0, and Q, x is greater than 0, are they equivalent?
One of them is an implication of the other.
But they have to imply, the converse has to be implied as well. So you have to have, equivalence only happens when one implies the other and the other implies the first one.
So then if one implies one, but the other doesn't,
it's an implication between two statements, because that implication might not even exist. So that might still be important to you, but it doesn't prove equivalence. Okay, and equivalence is, it's basically, when you go back to that algebra, equivalence is stronger, but it's that idea that two things are definitely equal. In fact, a good example of equivalence is from your work that both classes are doing on the unit circle at the moment. Tan theta is equivalent to sine theta over cos theta. Now, it's not proof, so they're actually called identities. So I haven't used it yet, but the other class may have seen a triple equals sign. That's an identity, and I will introduce that at some point in my class. But basically that's saying tan theta is identical to sine theta over cos theta for any theta. That's kind of the same thing as equivalency. So for any x or y here, is this true? And we showed that it wasn't. So they're not equivalent. So B...
Oh, the Q with the line in it does not apply. No, what's the Q with the double line?
Is that all right, Jamie?
Hang on. Oh, the Q with the double line.
You could copy it down a bit later if you need to.
Okay. It is... Q with the double line? Oh, God. Wait, what's the Q with the double line?
A Q with a double line is rational.
Are we going to need to remember that?
Yes. Okay. So P, the statement Q x cubed is greater than 0, and Q, the statement x is greater than 0. Let's have a look at, first of all, the first equivalency. Does P imply Q? So if I start with x cubed is greater than 0 is definitely true. And let's say that x doesn't really say anything, but at the moment all we know about are real numbers and down. So let's just say x is a real number. Does x cubed imply that x is greater than 0? X cubed is greater than 0. Why?
Yes.
Because if it's a negative, you get a negative answer.
Yeah, therefore it's not greater than
That means
zero.
it's not greater than 0.
Okay, so why don't we do it like this?
Positive, then the starting value has to be positive.
Let x equal a such that a exists in the real numbers positive. Okay, so first of all, we know this is x cubed is greater than 0, so we're not dealing with equals 0. So let's start with that. But let's say x equals a such that a is a positive value. If x equals a, then x cubed equals a cubed, and a cubed is also positive, but equally, actually I should really swap this around. So I'm going to swap this around because I've got the wrong way around, but you're going to see where we're heading. X equals a cubed such that a cubed is a positive, then x cubed is equal to a cubed, then x is equal to the cube root of a, and the cube root of a positive is also positive. So we've got that statement. We know that if we cube root a positive number, we get a positive. On the other hand, case 2, let x cubed equal a cubed such that a cubed exists in the real negative numbers, so the negative real numbers. Then when we take the cube root of x, that is the cube root of... so that's not right. That should just be a, sorry. And that should just be a. So I'm making these statements there. Therefore, x equals a, and a will also exist in the real negatives. So when we cube root a negative, we get a negative. We know that's true. And so this works. And the other statement we need to make, this is case... What do I write there? That's 1. 2, does Q imply P? And we get the same thing. If x equals a, such that a is a real positive, well, we know that x cubed equals a cubed, and a cubed will also have to be a positive. So if we cube root a positive, so if we cube a positive, we get a positive. And equally, so that's case 1. And case 2, if x is equal to a, where a is a negative, we could also just do negative a. In fact, I'll do that for this one, just to show you. You could say, if x equals negative a, then x cubed is equal to negative a cubed. And negative a cubed is a real negative, and that doesn't really matter. All that matters is this one here. So the implication holds both ways. And so therefore, P and Q are equivalent. Now, you might still be grappling with trying to make elegant proofs, and to be honest, I think maybe I could write that one a bit better, but the first one's all right. My suggestion will be, it's a little bit like some of those maybe harder questions you get in probability or something like that. You might or like a 3D trig question, for example. You're probably going to smash out something that looks terrible. You can have a rough diagram, you can try and work out what's going on in the diagram. You might do a couple of things wrong first before you find the right path. Do the same thing with these. Just try and find that link. Once you've got it right, then practice writing it out elegantly. So I might actually fix this one up in a minute so you've got an elegant variation on this. Are there any questions?
I wasn't sure.
Yes. How does negative a cubed